Hello dear students, welcome back to my channel and welcome back to power system class. In this video series, lecture series, we are discussing the basic principles of power system, and in previous lecture we have seen the basics of delta connections, star connections, and the transformation, that how we can convert the delta transformation into star transformation. And today we are going to see how we can convert the star transformation into delta transformation, which is basically known as star to delta transformation. Okay, so in order to understand what is star transformation, delta transformation, if you haven't seen the previous video, I would recommend you to um, see the last lecture. The link will be visible on the I button. It will be flashing over on the right top right corner of your screen. So if you've already seen it, let's start the proceedings with the star to delta transformation. But again, if you haven't seen it, I strongly recommend you to see that, because uh, without knowing delta to star transformation, it will be very difficult for you to understand the star to delta transformation, because it is nothing but continuation of the previous one. So let's come to the topic. Let's start star to delta transformation. So as we have seen in previous video, this is a star connection. It has three branches, or you can say um, three different streams. See, R1, R2 and R3, which are connecting at here at a junction point, which is known as neutral. And we have delta connection, in which all three of my resistance are connected with each other directly. Now in order to convert the star into delta, we have to go back and see what we have done in delta to star. So let me take you back from delta to star. This what we have derived in the previous class. We have derived the value of r1, r2 and r3 for delta to star transformation. So if I want to find the value of r1 while converting, r1 of star, r1 is always in the star. Remember, whenever you have a r1, r2, r3, they are in star, and whenever you have r12, r23, r31, they are in delta. So when you are converting delta to star and you have r1, which means it will be of star side. So um, these values we have derived, we have came up with values of r1, r2 and r3. Now in order to convert this star transformation to delta transformation, what we will do, we will go reverse. So now let's try to multiply the values of r1 and r2. Okay, if I multiply the values of r1 and r2, what will I get? I will get the multiplication of r12 into r31 into r23 into r12 again. See, here we have r12 again. So we will get these. Now this will be my numerator. Now in denominator, what will I get? Denominator is same, right? r12 plus r23 plus r31. Okay, so what will I get will be whatever the result, it will look like something like that, something like this. See, r1 into r2, we are taking multiplication, right? Let me go back there again. Here, r1 into r2 is equal to r12 into r31 divided by r12 plus r23 plus r31 into, this is the value of r1 and this is the value of r2, r12 into r23 divided by r12 plus r23 plus r31. Now we have we are multiplying, right? We are multiplying, so numerators are same, so it will be squared. We will get the square of the, sorry, denominators are equal, so we will get the square of the denominator. And in numerator we are having r12 twice, so we'll get r12 square and then r31 and r23 as it is here. See, so again similarly what we will do this time, we will multiply r2 with R3. So let's again go back to delta to star and see what was the value of R2 and R3. So R2 and R3's values were R23 into R12 divided by I'm talking about R2. So it was R23 into R12 divided by R12 plus R23 plus R31, and the value of R3 was R31 into R23 divided by R12 plus R23 plus R31. Okay, so that was these were the values of R2 and R3. Now multiplying them, what we will get? We will get R2 into R3 is equal to R2 into R3 is equal to R23 into R12 into R31 into R23. So here R23 is repeating twice, right? And the the denominator will be R12 plus R23 plus R31 into R12 plus R23 plus R31, which means denominator is similar, so again it will get squared, and in the numerator part what will be get squared? R23 will be get squared, and R12 and R31 will remain as it is. So let's verify it. Is it? So yeah, R23 is getting squared, R12 and R31 remains as it is, and denominator is will get squared. Now again, let's take the multiplication of R3 with R1. So when we take multiplication of R3 with R1, what we will get? R3 into R1 is equal to R12 dot R31 into R31 into R23. So here you see R31 is getting repeated twice, and again denominator same as the previous two cases, the denominator will get squared because it is same. So I'm sure you would be able to grasp whatever is going on. So let's verify it here. R31 square into R12 into R23 divided by R12 plus R23 plus R31 whole square, right? Now what we will do, we call this multiplication of R1 into R2 equation 10, we called multiplication of R2 into R3 equation 11, and we called multiplication of R3 into R1 equation 12. Now we will take summation of all these three equations and we will see what we will come up with. Okay, so what will we get on the left hand side? It will be R1 into R2 plus R2 into R3 plus R3 into R1. Let's verify the left hand side first. See, R1 into R2 plus R2 into R3 plus R3 into R1. Now coming to the right hand side, there is a trick. Okay, the denominator is equal. We are taking the summation and the denominator is same. So denominator will be will remain the same, right? So denominator, see the denominator is remaining the same. Now what will happen with the numerator? That we will be having, if you see in all three, what are we having common in here? What is the common factor among all three equations? It is R12 into R23 into R31. It is common in all of them. See, but in the first equation R12 is getting repeated twice, in second equation R23 is getting repeated twice, and in the third equation R31 is repeating twice, which means it is getting squared. So can't we take R12 in dot R23 dot R31 common and keep the R12 plus R23 plus R31 in the bracket? So that is what we have done here. We have taken R12 dot R23 dot R31 common out, and we kept R12 plus R23 plus R31 in bracket. Just to make sure, you can also multiply all three of them in here, and if you will get the same values which we will get if we didn't skipped one step, right? We skipped one simplification step in here. So we are getting R12 dot R23 dot R31 into summation of R12 plus R23 plus R31 divided by the square of r12 plus r23 plus r31. Now you see we have the same values in numerator as well as denominator, r12 plus r23 plus r31 and r12 plus r23 plus r31. So can't they will won't they cancel each other out? So they will cancel each other out, and what we will be left with? We will be left with uh, out of these two values it was square, right? So we will left with one value, r12 plus r23 plus r31. It is not squared, only simple value. Okay, and in numerator we will be left with r12 dot r23 dot r31. Now let me take one thing here. If I put bracket over these, what I get, like if I'm separating r12 away and I'm putting r23 into r31 and divided by r12 plus r23 plus r31. Can't we do that, right? We can do it. So when we do it, we will get this value, r23 dot r31 divided by r12 plus r23 plus r31. So doesn't this equation looks a little familiar to you, right? We saw this equation while deriving delta to star transformation. So let us go back and see what was the value of this. If you have seen the video, the previous video carefully, you will be able to tell what was the value of this, right? What was the value of this? This is the value of it will be r3. But even though, let me go back and show it to you also to verify. So see, what is the value of r3? It is r31 into r23 divided by here only, see, okay, on the bottom right corner. Okay, so r3 is equal to r31 dot r23 divided by r12 plus r23 plus r31, right? Now let me come back to what where we were, right? So r23 dot r31 divided by r12 plus r23 plus r31. So the value is similar, so can't we write r3 here? So we just wrote simply r3 instead of the whole value. So by the way, we are not doing any changes on the left hand side, so left hand side is as it is since the beginning. Left hand side is as it is. So we are having r1 r2 plus r2 r3 plus r3 r1 is equal to r12 into the value of this equation was r3, so r3. So here we are getting that equation only. Now if I want to send this r3 on the other side, what will I get? I will get r1 into r2 divided by r3. Here we are having r3, so r3 will cancel each other out and we will be left with r2. Again we are having r3 here, so r3 will cancel each other out and we will be left with r1 is equal to r12. Okay, so that will be the value of r12. R12, the resistance which was on the right side. Let's go back to this here. See, this will be the value of r12, this resistance. Okay, so that was the derivation of the first value. Similarly, if you recall what we have done in the delta to star transformation, can't we do a little bit similar thing here? Can't we be a little smart and do this? Like if we are having r12, what we are doing, we are taking the summation of r1 plus r2, which means the resistance which are connecting node 1 and node 2. R12 is also the resistance which is connecting node 1 with node 2. Okay, so we are taking the summation of those two, r1 plus r2, plus we are taking multiplication of r1 r2 and we are dividing it with r3. What is r3? R3, which is the resistance which is the not connecting node 1 and node 2, is it's connecting other nodes. Okay, so we will divide it by there, or even in simple words, what we are doing, in order to find the value of this resistor, what we are doing, we are taking simple addition of these two, r1 and r2, and what we are doing, we are adding the multiplication of these two, which is divided by this r3. So if I want to find the value of R23, can't we do the same thing, right? Can't we do the same thing? So and even if you want to find the value of R23, we can we can put the value of R12 in here back. What was the value of R12? This is the value of R12, right? So this is how we derived the value of R12. So we can also put the value of R12 back in here, okay, in either of this equation, and we can derive it. But if you're smart enough, what you will do, you see here the pattern R1 R2. So we are R12 is having two numbers R1 and R2, so we are having R1 plus R2, then multiplication of those two numbers divided by R3. So if I want to find the value of R23, what will be the equation? It will be R2 plus R3, multiplication of both these numbers divided by R1. If I want to find the value of R31, what will it be? R3 plus R1 plus multiplication of both those numbers divided by R2, right? Simple enough. So by doing that, we can find the values of all three resistors in the on the delta side, and this was nothing but your star to delta transformation. Don't worry, this was only derivation, so you will need the reference from delta to star while derivating star to delta transformation. But that is not the same case with the numericals. Okay, when you go for the numericals, the things will be changed. Okay, so while going for numericals, I recommend you to remember this, not all these three equations, but this pattern which we have formed. Okay, so when you want to convert the star into delta, what you will want, the value of R12 will be, or value of Rxy will be Rx plus Ry plus Rxy divided by Rz. Okay, or if we are taking R123, then it will be R12 is equal to R1 plus R2 plus R12 divided by R3. Okay, similar pattern you can find in the delta to star transformation as well, which we have discussed. See, what was the value of R1? R1's value was R12 into R31 divided by R12 plus R23 plus R31. So in the R1, the denominator was the sum of all three branch resistors of delta connection, but the numerator was the multiplication of only the two connections which were directly connected with which were directly significant with R1. See, R12 and R31, both of them having one in it. Okay, R23 is not here. Why? Because it is not having one in it. So if you identify the pattern, it will be easy to remember the formulas, and uh, you will be easily able to do the sums related to star to delta transformation or the delta to star transformation. Okay, so that was the star to delta transformation for you. Now we will be moving forward with the another topic which I want to discuss today. It is called per unit, or per unit values, or percentage method. Let's straightly dive into that. So simply, what is a per unit value is, um, if you want to find, if you are let me tell you, if you have a system, okay, you are having a whole system with whole power system with a large substation, and you are having uh, so many different components over there. Okay, so many transformers over there which are having different ratings. You are having CT, you are also having CTPT, you are having power transformer, and you are having everything. Okay, but uh, all those transformers will be having uh, different ratings, right? There is no way that all these transformers will be of the same rating. So in order to bring them on a common ground, what do? We do per unit measurement, or we use the percentage method. Okay, how? Let's see how. Okay, so this per unit method, it is adopted to bring all the parameters and components in power system to a common base. Okay, just to bring all these parameters to a common base, as I've said earlier. Okay, and the base value which this common base which I'm talking about, the base value, this base value corresponds to 1 per unit in per unit system, or 100% in percentage method. Okay, so it is all same, like suppose you are having a substation, and you are having transformers of different ratings. Okay, and uh, you choose a transformer, you choose a base kVA of transformer as like 100 kVA. Okay, so if there is another transformer 100 kVA, then its per unit value will be 1. Okay, and the percentage will be 100%. Okay, let's take another example just to make it more clear. Let's suppose we choose 400 volt as a common base. Okay, common base, common value, you can call it whatever you want, common base or common value. So this 400 volt we took common base, it corresponds to 1 per unit. Okay, or 100%. So now all the other voltages which we take, all the other voltages and present in that same system, we can convert them with respect to this base voltage. Okay, simply we can convert them with respect to this base voltage. Okay, so what will be the formula of the per unit voltage? It will be the actual value divided by the base value. So if I say there is another voltage source in the same system which we were just discussing, the actual voltage it is having is 200 volt. Okay, it is 200 watt. So what will be the per unit voltage? It will be actual voltage which is 200 volt divided by the base voltage. What did we took for the base voltage? We took 400 volts. 200 divided by 400 then equal to will be zero point 0.5. So my per unit voltage will be zero point 0.5. Okay, and always remember, when you are going for per unit values or percentage values, your quantities will not have any unit. Your quantities will be unitless. See, because your actual voltage is getting divided by the base voltage, which means your quantities will be unitless. Okay, so instead of writing voltage for unit, we write pu or per unit. Okay, so it will be 0.5 pu or 0.5 per unit. We will see the example at that time. I think you will be more clear about it. But at the same time, let's take the percentage value. Okay, so simply, what is a percentage value? Percentage value or percentage quantity is nothing but the uh, multiplication of per unit value with 100. It is as simple as that. So if you want to find the value of percentage voltage, so what we will do, we will take the per unit voltage and we will simply multiply with it. What is the value of per unit voltage? It is actual voltage divided by base voltage. So we wrote, what did we write? We write actual value voltage divided by base voltage, which is nothing but per unit voltage, into 100. So that will become your percentage value. Now let me come to one interesting thing here. If you have used reactance diagram or such things, so the percentage reactance value in those reactance diagrams are given, like generator G1 has having generator G1 is having 10%, G2 is having 15%, then transformer 1 is having 10%, transformer 2 is having 12%, like that. Okay, so these percentage reactance values is a these values are mentioned for uh, the calculation part of short circuit faults. If you want to calculate the short circuit fault, then we use this percentage reactance values. Okay, so if you want to find the percentage reactance value, okay, percentage reactance value based on on current voltage and the actual reactance that is given, the formula of it is percentage x which is percentage reactance, is equal to Ix divided by V into 100. Here uh, uh, I in the Ix divided by V is nothing but your full load current. Okay, I is full load current. X is, as I mentioned, the actual reactance per phase. We are talking about phase only, yeah, here, so don't get confused. We're talking about phase only. So I is full load current, X is actual reactance per phase, and V is the rated phase voltage. And we are simply multiplying it with 100, and what you will get will be your percentage reactance. Okay, so what it will be showing us, what is the reason behind finding this percentage reactance? Okay, not only the short helpfulness of it in the short circuit calculations, but it also indicates you that how much total voltage is dropped in the inductance. Okay, how much total voltage is dropped in the inductance when the what we say full load current will be flowing from your circuit. So whenever it will show you how much voltage is dropped from the inductance when the full load current is flowing from your circuit. Okay, so that is your percentage reactance. So I hope it is clear for you to per unit. uh, we can know more about per unit and percentage method using the examples. But before go diving into examples, I would like to tell you that the uh, not only voltage, current, or reactance, but you can find the per unit values of almost every electrical quantities. Okay, not only electrical quantities, you can find per unit values of almost every quantity. Okay, just to bring them on a similar common base or common ground. Okay, so same ways we can find the per unit current, which will be actual current divided by base current. You can find similarly per unit kVA. You can find similarly per unit reactance, which we just found. You can find per unit impedance. Okay, per unit resistance. You can find all of them. Okay, by one value or another. And after finding per unit values of them, we can also convert it in the percentage by just simply multiplying it your per unit value in with 100. So we can find the percentage of all these quantities as well. So I think we will keep this lecture till here. In the next lecture we will be discussing about the numerical, and we will be seeing uh, that how do we select the base value. Like I've said in while discussing the per unit values, that let's take 400 as the voltage base. Okay, so how do we decide what will be the voltage base or the base of your per unit value, per unit quantity? Okay, so we'll be seeing that in the next lecture. And the next lecture will probably end the basics of the power system, basic principles of power system. So we will be diving more deeper, and we will start with a new playlist. So I hope you all are ready. But in this lecture, we let's sum it up all here. I'll be seeing you in the next lecture. Thank you for watching. Take care. Goodbye, everyone.